Good morning, folks. Yeah, I did unmute. All right. All right. Welcome back. So I would like to start with this warm-up. It is a definite integral from x equals 0 to x equals 3. So those are the two provided x values of the function, integral of the function 2 to the x power dx. Look, the question is technically always asking about an area. We just won't use traditional area formulas like for a triangle or circle or something like that to find this area because this 2 to the x is an exponential curve. It really is a curve. There's a non-straight side to this. And so trying to use like a 1/2 base times height thing isn't going to work out. What we're instead going to do is separately look at the indefinite integral. So the question in the warm-up is asking about a definite integral, but we're going to take a moment and look at the indefinite integral. Now, it's sometimes the temptation is to take this and say that it's equal to this over here. These are two different things. There's a definite integral, there's the indefinite integral. They're related to each other. We're going to make use of them. We're going to make use of how they're related right now, but they are different things. So the definite integral is eventually going to be a number. This indefinite integral, as we see here, it's we've got a function with a plus c. So what's the integral of 2 to the x? So this is one of those pre-substitution integral rules, right? The integral of 2 to the x over ln of, the integral of 2 to the x is 2 to the x over ln of 2. And then there's this plus c. So there's actually many functions that work as an antiderivative. You can pick c to be 1 or 2 or 3 or 8 or whatever you want for c. The most convenient antiderivative is just going to be this part alone right there. So we'll use this in this next part as we look at, now we can look at the original question. So I left some space here just so that kind of these things align and we can kind of see better what's going on. But we have the definite integral. Now we're back to the original question. I'm going to use the most convenient antiderivative. That's when we replace the c with a 0. So the plus c is still required up here. But taking that antiderivative, you might skip writing this notation with the vertical bar, but I think right now it's kind of convenient to see. I took that antiderivative, the one where we plug in c is 0, it's written right here. And then there's this vertical bar, and 3 is written above because the 3 was above here in the integral. 0 is down here, so we have this 0 down here. Now the important thing about this vertical bar notation thing that we saw new last Wednesday is to make sure to plug in this upper x value first. It's just what happens. So we'll plug in x equals 3 first. You have 2 to the third over ln of 2 minus, then plug in the other lower x value here, 0 next. So you have 2 to the 0 over ln of 2. As far as work goes on paper, I think this is fine as a final answer. However, there's an opportunity just to simplify further. So just to talk a little algebra really is all. This first numerator is 8, yeah? And then 2 to the 0th is actually 1. So this is an 8 over ln of 2 minus 1 over ln of 2. Since we already have the same denominator or a common denominator, let's just write that as a 7 over ln of 2. Okay, again, I'm not expecting that you'd have to do this here in this situation. I think this is fine as a final answer, but I thought it's a good opportunity to go, put in this like, hey, common denominator business here. So the key thing is, while the original question was about a definite integral, we take a moment, a little detour to talk about the indefinite integral because that's useful in completing the definite integral. The key thing to please be careful of is that a definite integral is going to be a number, right? This definite integral right here became this number, and it would be incorrect to set a definite integral equal to an indefinite integral. Anytime you do that, that's incorrect. They're just different things. And this indefinite integral was this antiderivative problem with a plus c tacked onto the end of it. So here are three things that are written that are examples of incorrect writing. So the first one's the most kind of obvious of the incorrects. Like, so here you have a definite integral, here you have an indefinite integral, and they've been set equal. It's real tempting going from here to there to write an equal sign, but equals does not mean the next step, right? I think sometimes that's the habit that students run into is equals. I just need to write equals because that's what the next step I should write an equals. Equals means equals, like things that are actually equal. And well, unfortunately, these things are not equal, so that's why this is incorrect to write. The next ones are a little harder to see, but they're actually just other versions of this same error. So here you have a definite integral on the left side. The right side is the result of an indefinite integral, right? This right side was right there. That's the result of an indefinite integral. So it's really the same problem. It looks a little different, but it's the same problem of setting equal an indefinite and definite integral. Even if it doesn't look like that in this middle one, it really is the same problem because you're taking a definite integral and setting it equal to the result of an indefinite integral. The last one is a backwards version of that. Here's an indefinite integral. And then take a look at what's written here. That's a number. That's this number. That number was the result of the definite integral. So all three of these shown in the red box down here shouldn't be written. These are all examples of setting a definite integral equal to an indefinite integral. Just one of the things I want you to just be a little cautious about. Today what we're going to do is we're going to look at definite integrals and substitution. So how do these things combine? And there's like one little extra thing to, I want to say be careful of. If you follow the method that I want you to follow, kind of one thing at a time, then you won't run into any issues. And in fact, today can be very nice in terms of topic. But before going there, let's just take a step back and say this. So you're given a definite integral problem. So you're given these two x values here, a and b, and you're given a function. Now the final answer to such a question should turn into a number. Let's say you've decided not to find the number using area formulas. Now, there's sometimes you have to, like in parentheses I mentioned here, there's sometimes you have to. There's sometimes a definite integral problem. The only way to do this is using area formulas. We'll look at examples, mention examples of this at the end of class today. So let's say you've decided to not do that, right? Though, like, so there's a moment of this is a decision-making process. There's probably no writing involved in this decision. You just stare at the f of x you have and then decide whether you need to use area formulas where that's the way you must approach it, or you're going to do something else. But let's say you've decided not to use area formulas. Then the only other approach we have is to look at indefinite integral. So here's the first bit of writing that'd be done, but write that indefinite integral on its own line. I say this on its own line to try to get you to not write an equal sign between the definite integral and the indefinite integral. Since you'd be looking at an indefinite integral, find the antiderivative. Don't forget a plus c is part of that process of finding the antiderivative. When you find this antiderivative problem, it might require U-substitution. It might not require U-substitution. It just depends on that integral problem that you're looking at. So use U-substitution if you need to, and if you don't, well then don't. And then, having done that on a new line again, I want to emphasize again here, don't set equal the work that was just done to this. Go back to the definite integral. Use an antiderivative of this little f of x. Now, we'll call it capital F just like we did last Wednesday. The most convenient antiderivative to use is when you pick the c to be 0. So on this line, when talking about the indefinite integral, that plus c is required. Then when it's time to apply the fundamental theorem of calculus, it's most convenient to pick c to be 0. So you apply the fundamental theorem of calculus, that is this definite integral problem, turns into the value, the y value, or rather, let's just say the output of your antiderivative capital F at two different x values, once at the x value b and once at the x value a. In fact, the first full example that we did that applied this process last Wednesday looked like this, and I asked you to write this down, and if you didn't then, or you lost where that's written, please write this down right now. We're going to make use of this in a moment. So integral from 4 to 10 of the function 3x squared dx. This equaled 936 from last time. Yeah, maybe you'll recall that last Wednesday when we did this process, I had commented that if you look at this by drawing this out as an area problem, there's three straight sides and there's this one curvy side due to the parabola y equals 3x squared. And so even though there's this curve, it's actually rather surprising that the final area was exactly, this whole number was exactly 936. That was a little surprising. Again, we will make use of this in a moment, like not directly in the problem, but to compare with something a little later. So I'd like to try this problem altogether. Integral 4 to 10 of the function quantity e to the power x over 3 plus, and then the plus 8 is not in the exponent. X over 3 is the exponent. Then plus 8, back in regular size font, close parentheses, squared, times e to the power x over 3 dx. Okay, so the thing to do, and we're going to do this problem twice actually. The most convenient thing to do is to write the indefinite integral. Right? Method 1. So here's our first solution to this. Indefinite integral. It's the same problem. It looks rather the same. It's not the same problem, but it's just removing the 4 and the 10. We're looking at the indefinite integral right now. Indefinite integral. So no 4 and 10 for the moment. We're trying to find an antiderivative. Okay. It turns out for this, a substitution is going to be what works best. So I'm going to pick u equals e to the power x over 3. Then the plus 8 is not part of the exponent. So e to the x over 3, then plus 8. We'll take a derivative. Now, when you differentiate u, there's two terms. I'll talk about the easier term first. 8 differentiates to 0, right? 8 is a constant, differentiates to 0. What about e to the x over 3? Well, the derivative is, first of all, there's an e to the x over 3, and then by the chain rule, you need to differentiate x over 3 and multiply that in. When you differentiate x over 3, you could apply the quotient rule, but if you just rethink about it, instead of differentiating x over 3, let's differentiate, not the derivative of x over 3. Let's think of it as the derivative of 1/3 x instead. And the derivative of 1/3 x is 1/3. That's where this extra 1/3 came from. Normally that 1/3 is written last in the chain rule, but I just switched the order here. Okay, so taking this derivative of u required the chain rule. That's where this extra 1/3 comes from. And then solve for dx. So you got to multiply by dx and then do some other steps. I wanted to spare you some details here. So when you isolate dx, you will end up with 3 times du over e to the power x over 3. So right here, let me circle it for a moment. But that is a power here. Sorry for how tiny it gets written. It's hard to see. But that denominator is e raised to the power x over 3. And that's what dx is. Okay, so we have a selection for u. We have dx isolated. Now we can substitute. So this indefinite integral problem I recopied right over here. And I did some substitutions. Yeah, so what was in parentheses got replaced with a u. We still needed to write the square to account for that. The dx that's right here got replaced with the fraction 3 du over e to the power x over 3. Hope that looks all right to everyone. As written here, this integral doesn't look all that nice because it's got this mix of x's and u's. I don't want to have two variables, but we're not done with what we can do here. Take a look. There's this e to the x over 3 in the numerator and 1 in the denominator. So those will cancel each other out. We're really left with integral 3u squared du. You'll notice in all the steps we've had so far, there's still this integral sign because we haven't found the integral yet. Or we have not found the antiderivative yet. Remember, this symbol means antiderivative of. When there are no numbers attached here and here, read this symbol as antiderivative of. So antiderivative of, now that the question is antiderivative of 3u squared du, I think we're ready to now answer what the antiderivative is. So now we no longer write the antiderivative symbol. The antiderivative of 3u squared is u cubed plus c. don't forget the plus c here in this step. And then, oh yeah, one last thing. Let's replace the u with e to the x over 3, then plus 8. The plus 8 is again not inside the exponent. So quantity e to the x over 3 plus 8, close parentheses, raised to the third power. That raised to the third power is to account for the cube that was still here. Then a plus c. Okay, that finishes this antiderivative problem. Right now, I will say that we needed to show all this work to see what's going on, right? But right now, I think the work is going to get in the way. So I'm going to summarize on the next line that we found this antiderivative problem, this indefinite integral. I'm going to skip the work right now. We had to show it, otherwise how would we have gotten here? But I've highlighted those two things in red, right? So this is equal to this thing, which is equal to that, which is equal to that, eventually equal to this. So I just took the two things in red and just wrote them here to summarize. So since the indefinite integral problem, after the work is all done, becomes this, now on a new line without setting equal here, we can go back to this original problem up there, and we should take this antiderivative and plug in, I've highlighted the x in red in fact here, plug in first 10 for the x, and that's written here. And then after a minus sign, plug in 4 for the x that's highlighted in red, and that's written right there. How does that look for everyone before we move on? Okay, I think if you take it one thing at a time, you look at the indefinite integral first, and then once you've found this, antiderivative plus c, you apply that over here to answer the definite integral question. I think this is the most convenient thing to do. So notice there's a lot of time spent not in the original question, in a related question. So all this work over here, actually, let's be even clearer about it. It's actually all of this stuff relates to the indefinite integral, right? So there's a lot of time spent with the indefinite integral. And then once that question is done, you go back and then apply this to the definite integral. There is another way to do this. This second way takes up more writing, in my opinion. You'll see. And yet somehow the second method is the one that students try to do the most often. So we have to go over it because people try to do this. I think this second method always takes up more time. It takes up more time because it takes more writing to write it. But we'll go through it because you got to see it. So look, it's going to be the same u, so same du over dx, same dx, but there's going to be this additional step. If x equals 4, so this x value 4 down here, we can find out what u is. U is going to be e to the 4/3 plus 8 because what you need to do is go to how we defined u right here, and you plug in 4. So you have e to the 4/3 then plus 8. Same deal. When x is 10, u will be e to the power 10/3 then plus 8. So we'll hold on to that. This method too stays with the definite integral the whole time, never moving to the indefinite integral. So the original question here, now take a look, what was in parentheses was u earlier, that still gets replaced with u. There's still the square like last time. There's this e to the x over 3 like last time. The dx gets replaced with a fraction like last time. The key difference you'll notice is this mess right here and there. Those are the correct values that need to be here. Here's the reason. This integral ends with a du right there. If you've got a du right here, you need u values here and here. The 4 and 10, which people tend to often copy over, those are x values. So we need u values, and that's why we took the time to compute some u values over here. So the moment you replace the dx, you no longer have dx, you'll have a du right here. You have this du, and so you need u values as the endpoints of your integral. These u values, are they more work to write? Yeah. And guess what? In the next step, as we cancel the e to the x over 3 on top and bottom, you still have to write these very long, painful to write down u values. So we'll do that again. Canceling the e to the x over 3's on top and bottom, you have this 3u squared du with these same u values. And then to make sure that we're not making the error of setting an indefinite and definite integral equal accidentally, since this should be a number, I found this antiderivative u cubed, but then using the vertical bar notation to list these two u values here, and then finally just plug in u is this upper value first, and then there's still the cube to account for, and then after the minus sign, this lower u value is plugged in next with the cube. So this number right here is the same final answer as we had just a moment ago using method 1. But you'll notice with all this writing here, this ends up, and it depends, I mean, this is even a short problem in some sense. Like, this ends up being a lot of extra writing. This is a good place to end this question, but to talk about what I want to talk about with this, I put this into a calculator, and I happen to get 45,000. Now, the confusion is usually about this. So let me say a word or two about what's going on here. And I'll say, look, since this integral right here, right? This integral has a du, right? It's highlighted in red right there. The endpoints of the integration, right? So where the 4 and 10 used to be in the original question up here, those are called the endpoints of integration. Those must be u values. So you'll see underlined here, those red things, those are u values. That's why we had to compute those u values. That's what this was about. That's why there was this extra work right here. We didn't do a step like this in the previous method, but we had to plug in 4 in right here to get the corresponding u value. So when x is 4, u happens to be e to the 4/3 plus 8. When x is 10, u happens to be e to the 10/3 plus 8. So we had to write those out, because we needed, when there's a du right here, we need u values in this spot, not a 4 and a 10. And in fact, the most common error is taking the original question that's right here, I've put that here, and then whether it's in this version or this version, I put this over here and then put the 4 and 10 is the common error that people tend to have here. The problem is this du and these, the 4 and 10 those are not u values, those are x values. And in fact, if you just give somebody, give a calculus student without giving this problem up here, if you just tell them, hey, work on this integral 4 to 10 3u squared du, they'll treat this like integral 4 to 10 3x squared dx, just mentally replacing both the u's with x's. And that's what we just did last Wednesday. That's the thing I reminded you of, that integral from 4 to 10 of 3x squared dx is 936. This 936 is very different from 45,000. Those are very different numbers. So that's the error that occurs. I mean, it is an error, but to really point out very much why it is an error, you've got to be very careful that if there's a du here, you need u values here, not x values. This version here, circled down here in red, the problem is those are x values. Okay, I want to pause for a moment, see if we're okay. I'm trying to really message this to say this method 1 is less writing, it's less prone to errors. If we were going to meet in person, I would be handing out a sheet of paper, so I have a link to it down here. Let me pull this up here. It's just a chance to go through another problem, really is what it is, but it's on a sheet of paper, so somehow there's something nice about seeing it all on a single PDF. So I've got here the integral from 3 to 5 of 2x over 1 plus x squared quantity squared dx. So the way I think would be preferred to do this is the preferred solution, or method 1 as it was called in the slides, is just look at the indefinite integral, right? And I wrote this indef to avoid having the equals between a definite and an indefinite. So I've done some U-substitution here. You can kind of go through and you eventually have -1 over 1 plus x squared, then a plus c. Then going back to the definite integral, that was the question that's centered at the top. That definite integral, applying this indefinite integral of -1 over 1 plus x squared, you need to plug in the 5 for x first and then the 3 next, and that eventually simplifies. I mean, look, -1 26 plus 1/10 is probably a fine final answer, but it eventually becomes 465. And I simplified this as 4/65 to illustrate what I want to in a moment. To show that method too, so here's the definite integral question. It's down here again. I'm going to scroll down just a little bit. Okay, so there's the problem again. Same u value, but immediately once you replace the dx and you have a du here, you need u values. So you'll notice the integral, the first integral, the original integral had a 3 and a 5, but those were x values, so we needed u values of 10 and 26. Now the work isn't as bad to get 10 and 26 here, because when x is 3, you do 1 plus 3 squared to get u is 10. The one we were looking at was a little worse. Yes, I get that, but there's still this work. There's this work to write down these things that you wouldn't have had to do in solution 1. And all that work was required because the integral ending in a du and the insistence of staying with a definite integral the whole time. Eventually, as you go through, you still get this same final answer of 4/65. The incorrect thing that tends to happen, though, is this, that people tend to take the original question, and though they do this substitution, and there's this du right here, the integral sign still, people accidentally keep a 3 and a 5. Those, I remind you, 3 and 5 are x values in this problem, not u values. And in the end, sometimes people recover and still get the same final answer of 4/65. But the problem really is if you gave somebody the integral 3 to 5, 1 over u squared du, or you gave them this, or this next thing, any of these three things that are underlined here, if you gave those to anybody, as a problem on its own, they won't get 4/65. I didn't work it out here, but they'll get 2/15 as a final answer to any of these three questions. So this is someone's attempt to stay with a definite integral the whole time, but doing so, you have to update to have u values. Or if you don't want to do that, here's a way to fix this incorrect thing that works, but I mean, this will be acceptable. I'll accept this as a correct solution, but it's extra writing. This is already more writing than method 1 anyway, and it's incorrect. But let's make this correct. So it says du here, and one way to fix this, one thing I will accept, is to write x equals and x equals here, and to do the same here, and then to do the same here. But this ends up being a lot of extra writing. Already, this acceptable version is more writing than the incorrect version. This incorrect version is an attempt to write less than solution 2. And the thing that takes the least amount of writing and has the least amount of chance of errors is this method 1 right here. So I'll do one more example in full, and I'll just do the method that I prefer you do, just because it's the least chance of errors occurring. So integral from 0 to 3 of the function x times e to the power x squared plus 4 dx. So the thing to do, and this helps, I mean, I've been trying to set this up all through, last time even. It's just, let's just look at the indefinite integral. So just indefinite integral, no 0 and 3 for the moment. Integral x times e to the x squared plus 4 dx. Then pick a u. This is an integral that should be done by u-substitution, so u is equal to x squared plus 4. du over dx is equal to 2x. Solving for dx, you'll have du over 2x. So we'll substitute these things in to the indefinite integral. Right, so the indefinite integral here has been copied down here. Replacing the x squared plus 4 with a u, replacing the dx with a fraction du over 2x. This integral has a mix of x's and u's. That doesn't look so good, but hang on, the x on top and the x on bottom cancel. So we end up with integral 1/2 e to the u du. Okay, now that there's not this mix of two different variables, now that the only variable is a u, this is the time to think about the antiderivative. Now remember that e to the x is its own derivative, so e to the x is its own antiderivative. So here we are actually applying an antiderivative. That's why there's no more antiderivative symbol after the equal sign. It's just e to the u is its own antiderivative. Okay, so copy the 1/2, anti-differentiate e to the u, and you get e to the u. Then there's a plus c, and finally replace the u. So we have 1/2 times e to the x squared plus 4 plus c. Okay, so there's the antiderivative, right? So the indefinite integral problem is done. So this, after all the work, becomes that, and then we'll use this portion of the antiderivative just because, so the plus c here is required, and here for that matter, but we will now take the circled portion and just use that as the antiderivative for the going back to the original question, back to the definite integral problem. So looking at this part alone, plug in x equals 3 first, and then x equals 0 next. So what you're seeing before the minus sign is this circled text plugging in 3 for x, and then underlined next after the minus sign is the circled text plugging in 0 for x. As far as simplifying work goes, I think that's fine technically as a final answer on paper, but just to illustrate a point, let's just simplify this as 1/2 e to the 13th minus 1/2 e to the 4th. Okay, common error. So I encourage you to use this method 1 of writing where you just always work with the indefinite integral off to the side for a while, and then when you're done with the indefinite integral, like we were here, then you go back to the definite integral. The common errors, like people, I guess, are trying to do this method 2 thing, but don't actually do that, is in a step that looks, I guess, a lot like this, they'll just keep the 0 and 3, but the problem is the moment you replace the dx, this says a du. The moment you replace a dx, you've got a du, and at that moment that there's a du here, you need not 0 and 3 because those are x values. You need u values. Those u values would be 4 down here, and then let's see, x is 3, 3 squared 9. 13. You need a 13 up here, right? So it's just, instead of a 0 and a 3, you need a 4 and a 13 because you have a du here. Same deal. It's the same problem in the next integral over. In trying to keep a definite integral the whole time and trying to do method 2, you couldn't have a 0 and 3 here because those are not u values. You need to compute the u values. 0 and 3 are x values. So to point out, again, if you try the method 2 thing, instead of this, what you need is this down here, right? The definite integral has a du, so you need u values instead of x values, and so those u values are 4 and 13. Okay. Again, I think this method 2, it's prone to a lot of accidents, lots of errors. It's extra writing, it's extra computation. I would just stick to method 1. It's way nicer. Less chance for errors, less writing overall. I think that's the way to go. I'm going to ask you to take some time to practice these. And the key thing about practicing these 4 problems is to use proper notation. I will comment that just like the exercises from last time where I posted some solutions this weekend, this link does work already. So you could click on solutions or just ask if you want a hint. Send a little message and take some time, practice these. Please try to be good about practicing good notation and build a good habit right now. And then some announcements at the end of class. right, sorry for the interruption. Let me just say that please do click on the link that's provided in the slides here. Also, there was a link for last Wednesday. Click on that. That one finally works. This last one looks a little strange, I know, with this e to the e power, but it is really a chance to practice some logarithm stuff, some definition of logarithm. That sort of stuff actually did have an effect for some folks on the exam, which, oh, by the way, I'm 75% done grading, so you'll get those back today. Yeah, the process, I have to do a process before I start grading now online, and that process only took an hour instead of 5 hours that it took last time to even start grading last time. So you'll get the exams today. But yeah, anyway, so sorry, I'm off track. The thing is, this last one looks a little strange. Yes, I get it, but try it out. Look at the key. Definition of logarithms is what's happening there. So just to step back for a moment, we've got you may be given a definite integral problem, right? So if integral sign two x values a and b, there's a function there, and it really is always a number. It represents area. Now, one thing you can do, one way to do this, just stepping back, is you can think of this as an area. Draw a picture. There are times when that's required. The only way to do a problem that looks like this is to draw a half circle. The only way to do it, if you have this absolute value as part of what's inside f of x, is you have an absolute value, is to draw that. So that's going to, absolute values is v shape. In this specific one, if you look at how this is, you can see that the only place this v shape should touch the x-axis is when x is equal to 5. The slope, then right where x is 5, you're going to have either a +2 slope or a -2 slope, either the coming in or going out right at x equals 5. So there's some details that I'm leaving out right now. I'm not working through these problems right now. I'm just pointing out that one option you always have is this signed area. Sometimes it's the only option. Very often, though, the other approach here works is where you, instead of looking at this question, look at the indefinite integral. And I really mean that, right? Like this method that we looked at today, where there's several different ways to write, but the most convenient way to do this is to look at the indefinite integral. Find an antiderivative, don't forget the plus c here, then apply the fundamental theorem of calculus. And then as far as finding the antiderivative goes, this text is a bit familiar, except I've updated it a little bit since last Wednesday, is we have these pre-substitution rules. So like this one people tend to forget a lot, but there's a way to do certain antiderivatives without even using U-substitution. So I'm calling those the pre-substitution methods. Sometimes what you have to do isn't one of these things right away. Sometimes you have to first rewrite the antiderivative problem. Maybe you have to take care of the fraction that you see. Maybe you have to FOIL or distribute or something like that first, and then you can apply these things. And then finally, there is the U-substitution approach. It's not the approach used all the time. That's why it's one of these co-equal triangular bullets here. Sometimes you do U-substitution, and I think that the point I want to make here, that this was the thing that was not stated last time. It wouldn't have made sense last time, but right now I want to say you've got to be very careful if you're going to write definite integrals the whole time through while doing substitution, right? You have to update the endpoints of integration. Instead of an AAB, as soon as you have a DU there, you're going to have different numbers. So that's a thing you have to be very careful of. I didn't do announcements at the beginning, so I'd like to do them now. And these announcements are a little longer because they include some additional information. So some usual things: quiz Tuesday, Thursday. Please keep current with Webwork, and what that means is don't start the assignment that is due today. I want you to start Webwork number 42 today. Monday, Tuesday, Wednesday, Thursday, I'll have the usual office hours. On Friday, I have some potential meetings, so I don't know when I could have office hours, so I'm just leaving that out for a moment. You could email for an appointment. What I am doing is I'm having Saturday, Sunday, and Monday office hours, an hour and a half in the morning, an hour and a half in the early afternoon. If you need additional times, whether it is on that Friday or Saturday, Sunday, Monday, email for an appointment, and I will try to, if I'm free, I will basically say yes, but you've got to, let me know. I'm just, I have certain drop-in times already is the point. So why these weekend hours? Well, our final exam will be available on Tuesday, May 12th, and needs to be turned in by the end of the day on May 13th. Now, it's the same kind of thing. It's instead of a 5-hour block of time, now you choose a 6-hour block of time. because officially the exam's 2 hours. I don't think it's even meant to take 2 hours. It's not twice as long as an in-class exam. It's maybe 1.5 times as long, if that, right? So same deal. I think this worked okay. Please turn in a single PDF file answering the questions in order and showing your work. I updated the final exam slide and made a copy of it right here. Originally, we were supposed to have an in-class final exam at 7:45 a.m. On Tuesday, May 12th. So that's why instead, on either Tuesday the 12th or Wednesday the 13th, in that 48-hour block of time, choose a 6-hour block of time in which to do the final. And I should also make this comment down here about keeping current with Webwork. What that really means is the last Webwork, I had to delete some assignments because we lost a week of the semester, of course. The last assignment that is for credit is Webwork number 44, and if you follow the dates that I'm suggesting you start, you'd start this Wednesday on May 6th. However, because the last two Webwork assignments are actually due early in finals week, I just decided let's just make them extra credit assignments. So if you don't do them, maybe well, they're extra credit. I would do them anyway since they are extra credit and they're relevant for the final. Yeah, I think let's leave it with that for announcements. See you tomorrow.